Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is Module 20 in my Computer Networks lecture series where I talk about the topology of the internet. And I've kind of, whimsically titled this module, It's Not a Cloud, right? So, we refer often to cloud storage or putting our photos in the cloud with this notion that somehow the internet is just a cloud, which means we don't really understand what it actually is. And we're partly to blame as the technical architects of the internet, because I've been to many conferences and seen many technical presentations where we do use clouds to represent networks. But obviously the internet is not a cloud, and I think one of the one of the mistakes that network instructors sometimes make is, diving into the details of IP addresses and Ethernet and Wi-Fi and all that kind of stuff, and sort of going through all the details, but not taking a bit of time to step back and say, okay, high level, big picture, what does the internet look like? If we were to draw the internet on a whiteboard, how would we draw it? And that's the purpose of this module. So I want to step back. I want to talk about the big pieces of how the internet fits together from a topology perspective, how those pieces are managed, how they're connected, so you have an idea of what the internet really looks like. And very specifically, how IP addressing and IP routing fits into that big picture, because the internet is doesn't just run on IP. So we're going to start our conversation at the highest possible level. At the highest level, the internet can be, or is, divided into a large number of big subnetworks called autonomous systems. And autonomous systems, which go by the acronym AS, are basically the large networks that are administered by a single entity. So an autonomous system is always managed by just one large organization, and these organizations tend to be governments or internet service providers, universities, and large companies. And each autonomous system is identified by an autonomous system number, or ASN. And the ASNs are administered by the IANA, or the Internet Assigned Number Authority. And these are the same folks that you'll remember also administer the IP address space. And autonomous system numbers were originally 16 bits, now they're 32 bits. And you might go, well, wait a minute, IP version 4 is 32 bits and we're running out of IP version 4 addresses. Aren't we going to encounter the same number with autonomous system numbers, or the same problem with ASNs? And the answer is no, because there's much fewer ASNs in the internet, because ASNs are not meant to address individual computers or devices like IP addresses. They're, again, meant to address or represent big networks that contain many thousands, or in some cases millions of devices. And just as an example of some of the organizations that would be given autonomous system numbers, the University of Calgary has its own ASN, AS33091. TELUS also has its own autonomous system number, AS852. And so if we were to draw a picture of what the internet looks like at the highest possible level, it would basically be a series of autonomous systems connected together. Now, when we're thinking about connecting and managing autonomous systems, there's two main classes or categories of protocol. The interior gateway protocols, or IGPs, are the protocols that are used to route packets between nodes within an autonomous system. And as we're going to see, IP is an IGP, one possible IGP. And the protocols used to route packets between interconnected autonomous systems are exterior gateway protocols, or EGPs. And the Border Gateway Protocol, or BGP, is the most relevant exterior gateway protocol today. And the devices that use BGP as a protocol to interconnect autonomous systems are, you can think of them as BGP routers, or more commonly we refer to them as BGP speakers. And so if we were to draw a picture of several autonomous systems, apologies for showing them as clouds, even though I said the internet's not a cloud, obviously even I'm doing it here. But each of these clouds represent an autonomous system, and these nodes are BGP speakers. And BGP speakers communicate with each other using the BGP protocol and exchange packets between autonomous systems. And of course, for the internet to work, autonomous systems do have to talk to each other. So the TELUS autonomous system, if it wants to access computers in the United States, needs to connect to autonomous systems in the United States, perhaps Verizon or other big service providers. If we want to send and receive packets from Europe, we need to connect to autonomous systems that exist in Europe. And the BGP protocol is used for all of this inter-autonomous system communication. How many autonomous systems are there? Remember, we were talking about how we've got autonomous system numbers are 32 bits. Well, there's actually not that many. Now, this slide is a little bit dated. It only goes up to 2013. But it gives you kind of an idea, ballpark, of how many BGP speakers there are. At the end of at the end of 2013, we had almost 450,000 BGP speakers in the world. And it's interesting to look at how the number of BGP speakers has grown over time, particularly when you look at the late 90s, early 2000s. This was the dot-com boom. And this was when high tech was booming. I remember this. I was just starting as a brand new engineer in the workforce during the dot-com boom. It was a very exciting time to be in high tech. And I remember the sentiment basically being, the internet is amazing. Let's build this internet. And, we were focusing on internet infrastructure, but applications had really not caught up to the infrastructure. So we were building all this network capacity, but nobody knew what the internet was really going to be used for. At that time, there was email, which was basically just memos in electronic form. There was web, which was just kind of a document retrieval system. And there was some file sharing, which, again, was just kind of like, sort of like changing floppy disks between people, but doing it, over remote distances. So most of the applications back then were basically electronic substitutes of existing applications that existed before the internet. And in many ways, it's kind of similar to when electricity was first introduced to the industrialized world. The very first applications for electricity were basically electrified versions of things that existed before electricity. So lamps, for example. People had kerosene lamps, now there were electric lamps. Heaters, people had fireplaces, now they had electric heaters. So the applications weren't really very different. And I remember going to technical conferences and people would talk about the killer app, the one singular killer app that was somehow going to justify all of this spending on internet infrastructure. And, it seems quaint even now to sort of think about there being, one killer app, because of course there wasn't one, there was thousands or millions of apps. And, I think, when we think back to, how technology and companies have influenced the trajectory of technologies, I really think Apple deserves a ton of credit for a lot of different reasons. But one of the things that Apple, I think, really introduced to the market was this notion of the App Store. So rather than there being one app, you just open up this platform, let thousands of people write literally millions of apps. And so the killer app wasn't one app, it was basically thousands. And in the early 2000s, when the bottom fell out of high tech, there was lots of layoffs. There was a lot of pessimism about high tech. But if you'll notice, the number of BGP speakers, the amount of internet infrastructure that was being built out, really stayed flat just for basically a year. And then after that, very quietly, it started to grow again. At a rate very much like what we saw during the dot-com boom. And, it just sort of goes to show that the internet never really went away. It sort of went away as a speculative stock market thing. But even after all that hype disappeared, it continued to grow. And now, of course, we think of the internet not as sort of the next big thing in stock market speculation, but really as a utility, right? I mean, we've got plumbing, we've got electricity, and we've got internet. And so that has basically been what has fueled the growth of the internet since then. And rather than all the hype being directed towards companies that built internet infrastructure, because during the dot-com boom, it was companies like Cisco, Nortel, Lucent, the people that were building the hardware that got all the attention. Now the attention is much more at the application layer, right? So the tech companies that people are excited about today, Google, Facebook, Apple, Amazon, they are the ones that are building the applications that run on the internet infrastructure. But of course, the internet infrastructure needs to continue to grow in order to support all of this activity. So essentially, we can understand the internet as a series of autonomous systems that are connected with each other and agree to exchange traffic, and in some cases, carry the packets from one autonomous system all the way through to another. So for example, there are many cases where autonomous systems don't contain the end user of the data, and they don't contain the servers that are generating that or serving up the data. They just basically serve as a transition point. So perhaps if there's a user in Mexico accessing a web server that's served in Canada, one or more autonomous systems in the United States would likely be involved just basically as an intermediate transition point for the packets being exchanged between Canada and Mexico. So this connection of autonomous systems together, or when you connect two autonomous systems together, it's something that's known as peering. And basically every autonomous system everywhere must peer with at least one, generally more than one autonomous system, right? Because the whole idea of the internet is global reachability. So if you have an autonomous system that's not connected to anybody else, it's obviously not part of the internet. It's its own closed off network. And interestingly, the connectivity used to peer two autonomous systems together is usually done using Ethernet, and the connections are physically done at institutions called Internet Exchange Points, or IXPs. And there are, as you would imagine, many IXPs around the world, some of them connecting or peering hundreds of different autonomous systems. You can look up IXPs on the internet to see where they're located, what they're named. There's the DEC IXP in Germany, Lynx in London, JPNAP in Japan, Equinix Ashburn in the US. These are just some of the older ones. There's lots more in existence today. Some of Canada's IXPs exist in Montreal, Toronto, Vancouver, Ottawa, lots of different cities. And this list is not exhaustive and it's not up to date because there are so many autonomous systems constantly being created and connected together. IXPs are growing as well. And you can think conceptually of an IXP as basically a big Ethernet switch that connects the BGP speakers for several autonomous systems together. And so the border gateway protocol it runs over top of Ethernet when these autonomous systems exchange packets. And so in my quest to sort of dispel this notion of networks being clouds, what do autonomous systems look like if we look inside this autonomous system cloud? Well, let's imagine, for example, an autonomous system that is an internet service provider like TELUS. So if we looked inside the TELUS autonomous system cloud, what we would essentially see would be a number of BGP speakers existing on the borders of the autonomous system. And then typically you have kind of a high-speed backbone network consisting of a series of very high-speed links. Almost always these are fiber optic links, usually high-speed Ethernet running over fiber. And these high-speed routers would be connecting cities together. There may be 3 or 4 of them within a major city, and they're meant to just take a huge amount of aggregated traffic and move it quickly from city to city. And then hanging off of these high-speed routers are a number of smaller, lower-speed subnetworks that are ultimately connected to users. Now, I've shown just one hop to a switch where we then have a user population. The network in most autonomous systems would definitely not be this simple. There would be a series of layers of Ethernet switches, subnetworks before you actually got down to the user. But you can conceptually think of these kind of user networks as ultimately feeding into these higher speed routers, with the last hop to the user sometimes being wired connections, like they might be within a company. If we were, if these users were like desktop computers where software developers were working, for example, the last hop might be a Wi-Fi connection within your home, where your Wi-Fi access point is connected to a series of switch layers administered by, TELUS or Shaw or whoever your internet service provider is. But again, at a high level, most autonomous systems have a very high-speed backbone network with, a few large routers. The University of Calgary has, I believe it's basically 2 paired main backbone routers in their network, and then all of the other subnets kind of hang off of those high-speed devices. So at this point, it's important to say a few words about how IP addressing works with autonomous systems. And so when we were discussing IP addresses, we talked about how, big chunks of IP address space are mapped to large regions. So for example, the network ID, the 8-bit network ID 136.0.0.0 has been assigned to Canada. And so, it's initially kind of confusing. Like if we have, network IDs that identify big, areas of the internet, and we have autonomous system numbers that identify big areas of the internet, why do we need both? And initially, autonomous system numbers, like, back in the ARPANET days, people weren't talking about autonomous systems. They were just thinking about network IDs being the only way to identify big networks within the internet. However, autonomous system numbers became necessary as the internet grew. So these days, if you look at any particularly large organization on the internet that operates a network, typically that organization will have several network IDs assigned to it. So for example, if you go onto the ARIN website and you look up TELUS, TELUS has a whole bunch of network IDs. And so autonomous system numbers were basically a way to kind of simplify the structure of the internet and say, okay, rather than trying to use network IDs, we're going to just map a single autonomous system number to a large organization and organize the internet that way. And so that also raises the question, how do IP addresses play together with autonomous system numbers. So let's consider, for example, maybe an internet user in Peru wants to access a server at the University of Calgary. And so that user's computer will generate an IP packet, maybe with address 136.159.12.4 or something like that. And that IP address will be forwarded, or that packet with that IP address will be forwarded to the edge of the Peruvian autonomous system where that user resides, and will be received by a BGP speaker node. The BGP speaker node will look at the IP address, note that it has the 136 8-bit network ID that corresponds to a Canadian computer. And basically what the BGP speaker then does is takes that IP packet, puts it inside, encapsulates it within a BGP packet, and gives that BGP packet the autonomous system number necessary to get that packet to Canada. And probably in this, for the cases of this example, the Peruvian autonomous system wouldn't have a direct connection to the Canadian autonomous system that contains the University of Calgary. Instead, perhaps it's connected to a Mexican autonomous system. And so the autonomous system number that the Peruvian BGP speaker puts on its packet would actually correspond to the Mexican autonomous system. It gets forwarded to the Mexican autonomous system. The Mexican BGP speaker looks at that IP packet and says, oh, this is a Canadian packet. It would then change the autonomous system number on that packet, most likely to send it to an American autonomous system. The American autonomous system receives that BGP packet, looks inside it, oh, this has a Canadian IP address, and then maybe the American autonomous system is directly connected to the Canadian autonomous system. And once the packet is received by the autonomous system that contains the 136 network ID, then it uses IP addressing within that final autonomous system to send the packet directly to the computer, the University of Calgary server. So that's how IP addressing sort of interfaces to the very highest layer of the internet. That's how IP addressing works with autonomous system numbers. Now let's think about how IP addressing interfaces with the lower layer of the internet. I don't think there's much debate that Ethernet is the dominant layer 2 technology. Maybe a combination of Ethernet and Wi-Fi are the two dominant layer 2 technologies on the internet. And so if we identify, and we know that Ethernet, for example, addresses frames using MAC addresses. So Ethernet doesn't know anything about IP addresses. And so how does the IP layer, and particularly IP addressing, interface with the MAC level addressing used by Ethernet? Well, this is done using something called the Address Resolution Protocol, or ARP. And ARP is a relatively straightforward protocol. If you start looking at Wireshark packet traces, within this course, within our GNS3 simulator, or just in general, you will often see ARP packets. And the purpose of ARP is to map IP addresses to MAC addresses, so Ethernet can be used to deliver IP addresses to the to particular computers. And so basically what happens is, if we go to the next slide, let's say that in this particular example, we have a router computer with IP address 192.168.0.1, and I've simplified these MAC addresses for the sake of this example. They are only they only have 3 characters. So the MAC address is for the router is 0C1. And this router is responsible for managing a subnet that contains 3 computers. Oops, actually I made a mistake here. This should be IP address 0.2, 0.3, and 0.4. And let's say this MAC address is 10, this MAC address is 0A, and this MAC address is 1B. Yeah, I just made I was cutting and pasting a little too much here. So all of these computers have different IP addresses and different MAC addresses. And so let's say that a packet arrives at this router and it is addressed to 192.168.0.3. And so this packet is going to this middle computer here. The problem is that the router communicates with the destination computer over Ethernet. And so it needs to figure out what MAC address it needs to use in order to deliver the packet to the computer with IP address 192.168.0.3. And this is where the address resolution or ARP protocol comes in. So basically what happens is the router is going to receive this IP packet, and then using the Ethernet broadcast address, which is all ones, it's going to send out a message across its Ethernet network saying, hey, who has IP address 192.168.0.3? That message is going to be received by all of the computers on the network, and the computer that has that IP address is going to reply back. And this middle computer will reply back with an ARP message saying, I have IP address 192.1 or .0.3, and my MAC address is 0CA. And so what happens then is the router creates an ARP table, and it will map 192.168.0.3 to MAC address 0CA. And so then it takes that IP packet, encapsulates it inside an Ethernet packet with address 0CA, and then sends that Ethernet packet through to the middle computer. The middle computer receives the Ethernet packet, passes it up the protocol stack, the Ethernet address or the Ethernet header is removed at layer 2, and then it gets sent up to layer 3 that takes a look at the IP address. So ARP is a very simple protocol. It's literally, hey, who has this IP address? And then somebody replies back saying, that's mine, this is my MAC address, and then a table is created that maps IP addresses to MAC addresses. And this table has a certain expiry time, so it'll stay valid for a little while, and then entries will be deleted and the table will be refreshed according to a particular timeline. And the last topic I want to talk about in this module is the domain name system, or DNS. And anybody who uses the internet, of course, on a regular basis knows that very rarely are we typing in IP addresses in order to reach computers on the internet. We tend to use sort of human-readable, character-based names. So for example, when I want to reach the University of Calgary website, I don't type in 136.159.whatever. I type in www.ucalgary.ca. And basically the purpose of the domain name system, or DNS, is to take these human-readable names and map them to IP addresses. This is done basically using a series of computers called DNS servers. And DNS is essentially a large distributed database that maps, names to IP addresses. And if you've ever configured a network interface by hand at a very low level, one of the pieces of information you always have to provide to your computer are the IP addresses of the DNS servers. So of course we can't have names like www.dnsserver.ca because we need the DNS server to map those things to IP addresses. So we always have to provide specifically the IP addresses of the DNS servers. And whenever we type in a name like this, it gets sent first to the DNS server IP address. The DNS server replies with the IP address of the machine that we're trying to reach, and then our computer knows to create packets with that IP address, and that's what gets generated and sent over the internet. And usually a large entity like a university campus or ISP will operate several DNS servers, 6 of them, maybe more than that. And as you can imagine, there is a hierarchy to the DNS system where if a local server can't resolve a particular name request, then that server is forwarded on to what are known as sort of root servers that have a larger database of names that they can draw on.